Hello everyone. In this video we will discuss about important concept not only for the inorganic chemistry but also in the context of organic chemistry. That is the idea of resonance. Now first we'll take a look at what is the concept of resonance, but the purview of resonance in inorganic chemistry is a little bit what should I say, limited to the specific case and examples. But in organic chemistry we will be able to again get an opportunity to study about resonance in detail. Okay, so what is this resonance? Now for molecules, right, based on the Lewis theory, we said we can draw the Lewis structures. But in some cases, right, what happens is a single Lewis structure may be inadequate for the representation of a molecule matching with its experimentally determined parameters. What is the meaning of this? Say for example, if we talk about the case of ozone, it will have a double bond between the central oxygen and the one peripheral oxygen, so we can just number them, so 1 and 2, and there will be a coordinate covalent bond. In this case, let us say we are giving the coordinate covalent bond between 1 and 3. Now the thing is, if you look at a single bond, the bond length will be what? 148 picometer. A double bond between the oxygen atoms, the bond length is what? 121 picometer. Now while in this representation we are giving a double bond between oxygen 1 and oxygen 2, we can also have an alternative structure. This is what we call as the alternative structure. We will be using another name for that little while. So this is called as what? Canonical structures, like that we call. Okay, so what is the alternative structure? Instead of having a double bond between the oxygen 1, central oxygen, and the second oxygen, what we can have? We can have a double bond between the oxygen 1 and oxygen 3, and this side we can have a coordinate covalent bond. Possible, right? Which means for the ozone we are able to give two representations, two Lewis structures we are able to give. Henceforth we will start calling them as what? Canonical structures. And ozone as such can be represented equally by both these structures. But when we are saying that ozone can have this structure as well as the other structure, right, what we are saying is that one bond in ozone will be having a length of 148 picometer. Other bond in ozone will be having 121 picometer. That is it, right? Single bond means 148, double bond means 121. But experimentally what is observed is something that has surprised many people. What is it? Experimentally, when they found the oxygen-oxygen bond length in ozone, right, they found that both the bond lengths are equal, and the value is kind of in between that 121 and 148. So double bond means 121, single bond means 148. Here what are we having? A bond length of 128, which is like intermediate between the single bond and double bond. Not just about the bond length, but the other bond parameters also, because about bond we said about what? The bond enthalpy, okay, bond order, correct? All these bond parameters, right, they found to be having intermediate values between that of a single bond and a double bond. So how do we explain it? Because one thing is, we say ozone can be represented either by this kind of structure or this structure, but in reality ozone is not having the properties either given by the structure 1 or given by the structure 2. Now how do we explain this observation? Because what we are observing is something that is there in reality, that ozone, both the oxygen-oxygen bonds will not be different, they will be identical. They will have same bond length, they will have same bond energy, and so on and so forth. Now the real structure of ozone which we are thinking about cannot be represented by a single Lewis structure, and what we will be able to do is only giving what are the alternative possible structures of ozone. As we can see, we are saying, either we can have a structure 1 or structure 2. What is the difference between the two? the arrangement of the bond positions. In this case, if you are numbering them, right, like 1 2 3, the double bond is between 1 and 3. In this case, the double bond is between 1 and 2. So only the bond positions we are altering. So these are the two alternative possible structures. And how do we indicate them? We'll indicate them with a double-headed arrow, like, one structure, second structure. We'll indicate them with a double-headed arrow. These structures that we are able to give for the ozone, right, we'll call them as what? Canonical structures, as we said before. We can also call them as resonance structures. What we can call them as resonance structures. Now, what is going to be the real ozone molecule? How do we visualize it? We cannot represent this with a Lewis diagram, but if you were to look at what could be the representation, right, we will have to have the bond length which is intermediate between the single and double, and what will be the bond order? Bond order also will be between 1 and 2. Now what is a bond order? Like, here we can talk about the bond order of 1.5, but bond order of 1.5 is not acceptable as per the Lewis theory, correct? So bond order 1 means what? 1 pair of electrons are shared. Bond order 2 means what? 2 pairs of electrons are shared. Bond order 3 means what? 3 pairs of electrons are shared. But bond order fractional value is something that we will not be able to see in the Lewis theory. But when we go to further chemical bonding theories, especially the theories which are based on the quantum model of the electrons, right, we will be able to also allow fractional bond order. So in molecular orbital theory discussions, we will see that we can have fractional bond orders also. They are also accepted. Okay. Now the visualization. So here if you see, it's like, if you have to express 1.5 bond means, single bond means we will put one line, double bond means we are putting two lines. 1.5 means we are indicating it like what? Dotted line. The second line is given as what? Dotted. But this can mean anything, right? If you put a single means a single bond, double means double. If you are putting one line and a dotted, does it mean that the bond order is 1.5 or 1.33? Because we will have examples where the bond order can be even 1.33. So this way we will not be able to clearly represent the hybrid. So the actual molecule is going to be what? It is going to be a hybrid of these two. The actual molecule is going to be like a hybrid, okay, of these two alternative structures, and the hybrid is what we also call as the resonance hybrid. The hybrid is what also we call as the resonance hybrid. Now what is the meaning of this word hybrid? To understand this in very simple words, right? Let us say we have a donkey and we have a horse. When we do hybridization, we are going to get mule. So if you want to understand mule, let us say we don't have the diagram of mule. We are not able to represent the diagram of mule. So what we are saying is, there is a horse and there is a donkey. So these are the two alternative possibilities. And the real structure what we have is what? The structure of that mule, which is the resonance hybrid. Okay. So resonance hybrid will have what? Partial characteristics coming from both these structures. Like in this case, it will have partial characteristics coming from both the horse and the donkey. Okay, some of its properties will be similar to the donkey and some of the properties will be similar to the horse. That is how a mule will get its properties. Now in the same manner, right, if you look at the characteristics in the structure 1, we see 1 and 2 there is a single bond. Structure 2, 1 and 2 oxygen there is a double bond. In the hybrid, it's going to be what? Between a single and double. So you get a hybrid bond. That's why we are saying the bond order is what? 1.5. Similarly here also you can see structure 1, first oxygen and third oxygen they have a double bond. Structure 2, first oxygen and third oxygen they have a single bond. The actual molecule will have a hybrid of these two. So that is how we are going to get the hybrid characteristics. And hybrid characteristics, we will not be able to represent them by using the Lewis diagram, because the Lewis diagram talks about only what? The conventional idea of having either a single bond, double bond, etc. The hybrid existence, right, is something that we will not be able to represent by the Lewis dot structure. That is why we will indicate all the possible alternative structures, and by keeping a double-headed arrow between them, and what we say, these are all the canonical structures and the real structure is going to be a hybrid of all of them. So that is how we will be talking about the resonance concept. Now resonance concept, right, is not just limited to the ozone molecule. We have various other examples including CO2. See, CO2, right, it looks very straightforward for us and simple. We talked about CO2 in the Lewis theory. So carbon will have basically double bonds, one with each of these oxygen. That is what will be the bonding in the case of CO2, which means what we expect is the carbon oxygen bond. This is the expectation. Okay, so we'll have double bond characteristics. That is what is the expectation. So what is the expectation? The carbon oxygen bond, so it will have what? Double bond characteristics. But what is experimentally observed is something different. Okay, the experimental observation is that the carbon oxygen bond length is found to be 1.15 angstroms, whereas in the carbon oxygen double bond, right, the bond length will be 1.2 angstroms. Means in CO2 the carbon oxygen bond length is found to be lesser than the carbon oxygen double bond length, and this can be only explained by using the concept of resonance hybrid. So how we will get the resonance hybrid existence in the case of CO2, that is what we are going to find. Okay, so if you look at CO2, one structure that we can think about is what? Carbon forming double bond with each of the oxygens. This is, we can say, structure 1. We can have alternative structures. So how we will be able to have alternative structures? If, say for example, we are having the carbon and there is a double bond with one oxygen. So here this oxygen octet will be completed. This oxygen octet will be completed. If this oxygen is forming a coordinate covalent bond, this carbon octet also will be completed. Okay, now this carbon can form a coordinate covalent bond with another oxygen. Observe carefully, what is it? Here we have the carbon forming a double bond with one oxygen. Oxygen octet is completed. This oxygen will give a coordinate covalent bond to the carbon. Coordinate covalent bond means what? Both electrons are going to come from oxygen. So by that the carbon octet also will be completed. Now this carbon has to bond to the other oxygen, right? It will be bonding through what? It will be bonding through a coordinate covalent bond. So what you see is the alternative structure, right, is carbon will have a triple bond with an oxygen. So here this oxygen is what? Donor. So as per the formal charge concept, right, it will be getting a positive. This oxygen is acting like an acceptor, means it will have a formal charge minus. So this is one possibility, we can call it as structure 2. The other possibility is what? We can just interchange the positions, right? We can have a triple bond on this side with a formal charge and a single bond on that side. So this is our structure 3. So what we see is in both structure 2 and structure 3 we are having triple bond characteristics. So if you look at the structure 2 and structure 3, right, the carbon oxygen bonds are getting what? Triple bond characteristics. So the real molecule CO2 will be existing as what? Hybrid. A hybrid of this 1, 2 and 3. Means the carbon oxygen bonds are going to be getting what? Partial triple bond characteristics. We can see in structure 1 both the carbon oxygen bonds are what? Double bond. In structure 2 one bond is triple, one bond is single. In structure 3 the other bond is becoming a triple and one that is previously triple is now becoming a single. So what you have is the bond characteristics will also have what? Triple bond characteristics, and that is the reason why triple bond characteristics means what? A single bond will be longer than a double bond than a triple bond. Triple bond is the shortest. Triple bond is what? Shortest. We have discussed about this in the bond parameters video. Okay, so since the bond characteristics will be hybrid, right, they will also have triple bond characteristics, means the bond length will be less than what is normally expected. Normally, what do we think of the carbon oxygen double bond? It is 1.2 angstroms, but in case of CO2, right, the bond distance is less than the carbon oxygen double bond, and this shortening is attributed to what? It is attributed to the triple bond formation in the canonical structures 2 and 3. Okay, because for CO2 we will not be able to really give what is the actual structure. Hence, what are we having? We are giving all the 3 canonical structures and then saying the original CO2 will be like a hybrid of them. Okay, so that is how we can explain why in case of CO2 the bond distance is less than 1.2 angstroms. Okay, now this is something, as we said, is of lot of importance when it comes to the organic chemistry, particularly the class of compounds which we call as the aromatic compounds, and one prominent aromatic compound is of course the benzene. Okay, so benzene, which has got the formula of C6H6, all benzene derivatives, naphthalene, anthracene, there are bunch of compounds which we are going to be calling as what? Aromatic compounds. Okay, we'll study about them in detail in the organic chemistry, but here benzene, right, with the formula C6H6 can be given by these 2 more stable canonical structures. So here you using the word stable, we'll talk about it a little while. Okay, so if you talk about the canonical structures, here they are giving us 2 canonical structures. What is the difference between the 2? Here we'll have a ring where there are of course 6 carbons in the ring. Okay, each carbon is bonded to 1 hydrogen, that is okay, each carbon is bonded to 1 hydrogen. Now inside the ring we have alternative double bonds. So you can see in the structure 1, if you are numbering it as like 1 2 3 4 5 6, between 1 and 6 carbon you have a double bond. Number them here 1 2 3 4 5 6. In structure 2, 1 and 6 we are having what? Single bond. Structure 1, between 1 and 2 carbons we have a single bond. Structure 2, what you are having? Double bond. So alternative positions, right? So we can either have this order where 1 and 2 is single, 2 and 3 is double, 3 and 4 single, 4 and 5 double, and 5 and 6 single, 6 and 1 double. Or what is the alternative possibility? 1 and 2 becomes double, 2 3 will be single, 3 4 is double, 4 5 is single, 5 6 is double, 6 1 is what? Single, like that. So we can give these 2 alternative canonical structures for the benzene. And remember this, we will discuss again. What are we saying? These 2 are more stable canonical structures of benzene, which means what? There are other less stable canonical structures also. There are other less stable canonical structures of benzene. Okay, so we'll talk about it in a little while. We'll look at them. Okay, what are those less stable structure? We'll look at them. But these 2 canonical structures, right, we'll call them as the Kekulé structures. So Kekulé structures will have what? The alternative double bonds in the ring. Now when you look at these 2 structures, what if you look at either of them, right, what we'll expect? Inside the ring we will have 3 carbon single bonds. That is what we expect, right? Inside the ring we'll have 3 carbon single bonds and 3 carbon double bonds. That is what we'll normally expect when you look at the structures. But in reality the resonance hybrid will not have this kind of an bond arrangement. All the 6 carbon bonds are what? Identical. So the resonance hybrid of these 2 forms, right, all the carbon bonds are what? Identical, and they'll have bond characteristics which are intermediate between a single bond and a double bond. The bond characteristics of the carbon bonds, right, all the 6 bonds are identical. So how again we can think about the resonance hybrid, right? And in fact, how do we represent the hybrid? We'll represent it like this. We'll put a circle inside the ring, we'll put a circle. That is how we'll indicate the fact that benzene will have resonance. Okay, now look at it. No, it is like what? Hybrid. In structure 1, between 1 and 2 carbons there is single bond. Structure 2, between 1 and 2 there is a double bond. Hybrid means what? The characteristics will be in between the single and double bond, like that. So this is how we'll have resonance in the case of the benzene. Now the idea of resonance, right, basically is like this. Whenever a single Lewis structure cannot describe the molecule accurately, means we are not able to describe the properties of the molecule, or the whatever the measured parameters, by using a single structure. Obviously we will have to look at what are all the alternative structures that can be possible for this molecule, and these alternative structures which will have almost similar energy, right, we will be calling them, of course, as what? The canonical structures. So when we want to represent the true structure of the molecule, which we cannot represent by a single Lewis diagram, what we'll do, we will identify what are all the alternative canonical structures, whatever the number it is. Okay, some cases we may have 2, some cases we may have 3, like that, and we'll arrange them with a double-headed arrow in between. Okay, so that is how we are going to explain the concept of resonance. So the actual molecule is supposed to be what? It is supposed to be a hybrid of all the possible canonical structures. So this is how we will have the concept of resonance hybrid. And there are a couple of important points. So one thing we said about the canonical structures is they will have similar energy. There are a couple of more things. The canonical structures, right, positions of atoms. In the canonical structures, positions of atoms or nuclei remain same. Means, look at it. No, when we have talked about the 2 possible bonding structures for the benzene, what is the thing that we have looked at alternatively? Only the bond positions. We'll say only the electronic arrangement changes. So when we are looking at the canonical structures, right, what will be the difference between them? Only the electronic arrangement will be different. The atoms positions or the nuclear positions, they will not be changing, they will remain as it is. And one more thing is the number of unpaired electrons. Among all the structures, the number of unpaired electrons is going to remain same. Why? Because unpaired electrons will be corresponding to magnetic properties. All the structures will have the same magnetic properties, and the number of bonding and non-bonding electrons, the number of bonding and non-bonding electrons also remain the same. So in the canonical structures, all the structures we see, the number of bonding electrons and non-bonding electrons also will be remaining the same. We'll discuss more about it when we go to the idea of resonance in the organic chemistry. Okay, because there we'll talk about how we will write the canonical structures for a given compound or a substance. But here some of these properties of the canonical structures will be important to know. Okay, now when it comes to the expression of canonical structures in the case of inorganic compounds, we have just one straightforward approach. That approach is what we call as finding out what are the alternative bond arrangements. Okay, so how do we draw the resonance structures for any molecule? If you want to draw the resonance structures, molecule or ion, whichever it is, if you want to draw the resonance structure, means what? We will have to find out what are the alternative bond arrangements. Like in the case of ozone, what did we discuss? We can have a double bond between oxygen 1, oxygen 2 and a single bond with oxygen 3. This is one possibility. What is the alternative possibility? We can have a double bond between oxygen 1 and oxygen 3 and a single bond between oxygen 1 and oxygen 2. These are the 2 alternative bond arrangements. Okay, so we will focus on what are the alternative bond arrangements. Based on that, we will be able to get the canonical structures. Similarly, in the case of say SO2. SO2 means what? Sulfur is there, double bonded to oxygen, and then coordinate bond with another oxygen. Here also you can see same pattern. Either this is the structure 1 possible. What is the other possible structure? We'll have so let us number the oxygens as 1 and 2. Here in this case we have a coordinate covalent bond with oxygen 1 and double bond with oxygen 2. These are the two canonical structures for SO2. Okay, in SO2 also, right, the sulfur oxygen bonds will not be different. They will be what? Having intermediate, because there is a resonance. The sulfur oxygen bond will have what? Intermediate characteristics. Okay, between the single and double bond. Okay, so this is what we will see in the case of the alternative structures. So how do you get the alternative structures? By looking at what are the different possible bond arrangements, and this is a principle that we'll use mostly when it comes to the drawing of resonance structures in case of inorganic molecules or the ions. We'll look at some examples of that. What is this question? Explain the structures of carbonate ion with resonance. Carbonate ion means what? CO3 2 minus. We'll explain the carbonate ion with resonance. In this, what is it? Okay, carbon is there. So already we have talked about the Lewis structure for the carbonate ion. Okay, so in the Lewis dot structures discussion, we have covered the carbonate ion. So carbon is bonded to 2O minus with a single bond and a double bond with an oxygen. This is what we have. Okay, so what is it? Carbon is bonded single bond with 2O minus ions and a double bond with the oxygen. Now when you look at it, right, what are the possibilities? The possibilities are that we can have alternative bond arrangements. How? If you think about it, right, let us look at it. Okay, let us call this oxygen as 1, this O minus as what? 2, and this is 3. Here we have a double bond between what? Carbon and the oxygen 1. You can have a double bond between carbon and oxygen 2. You can also have a double bond between carbon and oxygen 3. In that case, the other two bonds will become what? Single. So we have how many possible alternative structures? 3 structures we can have, isn't it? So either double bond between carbon and oxygen 1, or double bond between oxygen and carbon and oxygen 2, or double bond between oxygen, carbon and oxygen 3, like that. 3 possibilities. Accordingly, the other bonds will change. Correct. So the actual CO3 2 minus will be what? It will be a hybrid. The actual CO3 2 minus will be what? It will be a hybrid of these 3 structures. And the bond characteristics will be what? The carbon oxygen bond characteristics will be intermediate. The carbon oxygen bond characteristics will be what? Intermediate between that of a single bond and the double bond. Of course, we cannot show how the resonance hybrid will look like. That is the reason why we are indicating all the possible canonical structures and say that the actual molecule is going to be a hybrid of all these possibilities. Okay. Now we can also talk about the alternative possible structures for the nitrite ion. What is a nitrite ion? Means NO2 minus. In this, nitrogen will form a double bond with one oxygen and single bond with O minus. Okay. Now what will be the other possibility? If you are numbering the oxygens again, right, we are numbering them 1 and 2, means we can have a double bond with oxygen 1 and here it can be O minus. So we have how many? 2 possible alternative structures. Look at this. We have a double bond here between nitrogen and oxygen 1 and a single bond, or we have a double bond on this side and a single bond on that side. Remember, when we are representing the Lewis diagram, right, always we will try and keep the overall charge on the total entity. The charge will be kept on the total entity. Otherwise, we can also write it like this. Okay, so N single bond O minus double bond O. This is also accepted. Okay, so N single bond O minus. So if you write it like this as the 2 possible canonical structures, this is also accepted. Okay, so this is what we have in terms of the resonance phenomena that can exist in the case of nitrite ion. Okay, so we've seen both in carbonate ion as well as nitrate ion, right? What is the approach we are taking? First, we are trying to draw one Lewis diagram, and then we are seeing what are the alternative possible bond arrangements, keeping the atoms and nuclei as it is there only. We are not disturbing anything. We only try to see what are the possible alternative bond arrangements. That is it. When you do that, you will be able to get the alternative structures or the canonical structures. This is mainly the approach that we can take for all these inorganic molecules or ions when we want to understand the resonance concept. But when it comes to the organic chemistry, right, there we will talk about an idea which we call as the delocalization of electrons through a conjugated system. Okay, so this is the method that we will mostly use in which case? In the case of the organic chemistry. So there we will talk about this more importantly. But here let us just get a basic idea of what we mean to say by the delocalization of electrons through conjugated system. You know what is the conjugated system? Look at it. Okay, so you have a double bond. Okay, and alternative position. This is a double bond. Alternative position, you will have a cation, or you have a negative charge, or you have, maybe if not carbon, let us keep it some element X, you have a lone pair. So when you have a double bond, alternative carbon, you have a positive charge, alternative carbon, you have a negative charge, alternative carbon, you have a lone pair, or alternative atom, there is a lone pair. So such an arrangement, right, is what we will be calling as the conjugated system. Conjugation, we'll say in simple. What do we say? Conjugation. Okay, we'll say the double bond is in conjugation with the positive charge, the double bond is in conjugation with the negative charge, the double bond is in conjugation with the lone pair, like that we will say. Now what happens as a result of this is the electrons of the in double bond, right, one of them will be called as a sigma bond, other will be called as a pi bond. In a triple bond means one will be sigma bond, the other two bonds will be pi bonds. This we will learn in the valence bond theory. So where we will be learning about them? In the valence bond theory. What is a sigma bond and what is a pi bond? The electrons of the pi bond, right, in the double bond, the second bond will be called as what? Pi bond. Okay, the electrons of pi bond can be delocalized. So whenever you have a conjugated system, right, the electrons of the pi bond can be delocalized, and as a result what we will have is that the conjugated system, we will be able to have the alternative structures possible because of the delocalization of these pi bond electrons. Now what it is and in how many ways we can do it, all of this we will be anyway learning in detail when it comes to the organic chemistry. But here what we'll do is we'll just take one example and then explain. Okay, the rest of it we'll try to cover in the resonance with regard to the organic chemistry. So look at it, we have imagine, so there is a carbon having positive charge. By the way, you know what do we call it as? We will be calling it as a carbocation. Okay, and there is a conjugate system. So these are the pi electrons. The pi electrons can be delocalized here, means we will form a double bond, and as a result, right, so one of, see from here in the pi bond, one electron is for this carbon only, other electron is belonging to, let's number them now, 1 2 3, other electron is belonging to carbon 1, so it is taken out, it is taken away, and then that is used for forming a bond with carbon 3, which means what? Carbon 3 is getting the electron and carbon 1 is losing. So whatever the positive charge here, right, it will now be appearing on the carbon 1. So in the structure 1 we will call it as structure 2. We have shifted or delocalized the pi electrons. As a result, what is happening? In structure 1 we have a double bond between carbon 1 carbon 2. Carbon 3 is occupying a positive charge. In structure 2, between carbon 1 and carbon 2 we are now just having a single bond. Where is the double bond? Double bond is coming between carbon 2 and carbon 3, and positive charge is appearing on carbon 1. Okay, because of the delocalization of the pi electrons. Okay, so this is how we are going to look at the movement of electrons when we have the conjugated system. When you have conjugate system, this is how we will look at the movement of electrons. Okay, now we can take another example also. Say if you have carbon having negative charge in conjugation, you know what we will call it as? We will be calling that as a carbene ion. Carbon having negative charge, we will call it as what? A carbene ion. Okay, so look at this. if you have the carbon having a negative charge, double bond, so let us number them 1 2 3. Now the negative charge means what? Carbon is having extra electron. So if this is used for bonding, the electrons from here can be taken by the carbon. So you see, this is what we mean to say by the conjugation movement. As a result, what is going to happen? Look at it. You will have a double bond here, and the carbon one is now going to get a minus charge. So these are the two alternative structures. This movement is going to be possible when you have a positive charge or negative charge or a lone pair in conjugation with a double bond. Okay, so this is how we are going to get the possible resonance structures or the canonical structures in case of the organic compounds mostly. Okay, whether it is aromatic compounds or even otherwise, right? We will be using this principle of conjugation to get what are the alternative possible structures, especially the benzene derivatives. Maybe you can just make a note of it. When you are looking at the organic chemistry videos, you can take a look at it. Okay, benzene derivatives, right? When we talk about the resonance structures of benzene derivatives, particularly we will be using this concept of delocalization of electrons. We will use what? Delocalization of electrons through the conjugated system. Okay, so this is the approach that we will be taking in writing the alternative structures or the resonance structures to explain the existence of the resonance phenomena. So there are some important things that we need to keep in mind with regard to the idea of resonance. Now we said that for some molecules we can not explain all the properties by giving one single structure. So hence we are looking at what? We are looking at giving what are all the alternative possible structures and then say that these are the canonical structures and the real molecule is going to be a hybrid of them. But the point that we need to keep in mind clearly is that the canonical forms, they do not have any real existence. Canonical form don't really exist. If we say that mule is existing, mule is the reality, okay, that is the hybrid. Horse and donkey, the example that we discussed before, right? Horse and donkey, they don't have real existence. The real existence is for what? Hybrid. Okay, of course we are not able to show the hybrid on paper by using the Lewis structure. That is why we are indicating what are all the possible canonical structures and just saying what the actual molecule is going to be a hybrid of all of them, like that we are concluding. Okay, and the molecule does not exist even for a fraction of time in one canonical form or the other, which means what? It is not like you have for ozone, we say there are these two canonical structures, right? For ozone we have said these are the two canonical structures. The actual ozone, even for some fraction of time, it is not going to exist in either this structure or that structure. Canonical forms do not really have any existence, and there is not even this concept of equilibrium, because we will see in some phenomena, especially when we go to the organic chemistry, right, we will study about a phenomena called as tautomerism. What is the phenomena called as tautomerism? Okay, so if you have a ketone, correspondingly you will have a compound called as enol. Enol means double bond and then OH group. The ketone and enol, they will be having what we call as an equilibrium, and that phenomena is what is known as keto-enol tautomerism. Okay, so there what happens, you know, there will be equilibrium between the ketone form and the enol form, like maybe 70% will be in the ketone form and 30% will be in the enol form, like that. Okay, that is not the case in the resonance. It is not like, okay, this structure will have 50% existence, this will have 50%, not like that. The canonical forms are not the forms that will exist in equilibrium or anything. Okay, it is not like a phenomena like tautomerism that we learn in the organic chemistry. Canonical forms in fact do not have any real existence. And what is the most important thing? Look at it. The molecule as such has just one single structure, which is the resonance hybrid of all the canonical forms. And the thing is, this cannot be depicted by a single Lewis structure. We cannot put them on paper with one single structure. That is the reason why we are giving all these possible alternative canonical forms. Okay, and Other important thing, remember, when we talked about the resonance in the case of benzene, we said these two forms, we call them as what, Kekulé structures. We said these are the more stable ones. The point is, when you are drawing multiple possible alternative structures, all of them we call as what, canonical structures. So all canonical forms need not contribute equally to the true molecule. So we said it is a hybrid, like a horse and a donkey. You make a hybrid, you will get a mule. You'll have almost like what, 50% characteristics of the donkey and 50% characteristics of the horse. But it is not like, it has to be always like each structure has to contribute equally. Sometimes we can have different proportion of contribution, okay. And generally, what, the contribution is going to be depending upon the stability of the canonical form. So the stable canonical forms, they will be able to contribute more. Less stable, they will be contributing less. This aspect again is more relevant when we talk about the canonical structures of the organic compounds. So when we are discussing about the resonance phenomena in organic chemistry, we will talk about which structures are going to be more stable and which of them are going to be less stable. But the point we need to keep in mind is, among the canonical structures, the ones that are more stable, they will contribute more for the true molecule. The ones that are less stable, they will contribute less. Now how do we understand this? Okay, if you look at the case of benzene itself, right, we have already seen the two Kekulé structures. There are three more possible structure that we can give for benzene. What are these called as? Dewar structures. Look at them. We have a double bond here and here, and there is a diagonal bond. Let's number them. 1, 2, 3, 4, 5, 6. Diagonal bond is between 1 and 4. Here we have a diagonal bond between where? Between 3 and 6. Here we have a diagonal bond between 2 and 5. So these structures are called as what? Dewar structures. Now if you look at the contribution, right, the structures 1 and 2, which we call as Kekulé structures, their contribution will be what? 39% each. Means because they are identical, right? This will give 39%, this will also contribute what? 39% for the actual molecule. But the structures 3, 4, 5, these are the less stable ones, they are contributing only what? 7.3% each for the true molecule. Why? In Dewar structure, if you look at it, there is a diagonal bond. The diagonal bond electrons, right, are inside the ring. Where they are inside the ring. So what happens as a result of this? There will be repulsions acting in the ring, right? They will lead to what? Less stability. The repulsions, because if there are electrons inside the ring, means what? The other electrons, they will be what? All of them will be repelling it, right? So there will be more repulsions for the diagonal bond electrons. That is the reason why the Dewar structure will be less stable. Okay. So in organic chemistry, we will talk about lot of other factors on which the stability can be dependent upon. But the main point here is, it is not like each of these canonical structures has to make equal contribution for the true molecule. Okay. So the contribution will be based upon the stability. More stable canonical structures will contribute more. Less stable canonical structures will be contributing less. Okay. So this is what we need to understand about the contribution of the canonical structures for the actual molecule. Now whenever we have the idea of resonance, one thing that we need to keep in mind is that resonance as a phenomena will be stabilizing the molecule. What do you mean by stabilizing? The resonance hybrid which we are talking about, which is the real, like in the case of benzene, right, the resonance hybrid will have a less energy than any single canonical structure. See, let's talk about benzene itself. This is the energy axis. Okay, here what is it? This is the hybrid. What is this? This is the hybrid. These two are what? These two are the Kekulé structures. Other canonical structures means what? We are talking about the Dewar structures. Okay, so we see the hybrid is having less energy than any single canonical structure. It is having lesser energy than Dewar structures and also lesser energy than the Kekulé structures. Now we can even quantify how much stability the resonance is bringing to the molecule. The amount of stability that resonance is able to bring to the molecule is explained based on the energy difference between the hybrid and most stable canonical structure. Most stable canonical structure means what? The one which is having the least energy, isn't it? Because less energy means more stable. So we will have to look at, in case of benzene, the energy gap between the Kekulé structures and the hybrid. What is it? It is 30 kilocalories per mole. So this energy is what you call as resonance energy or resonance stabilization energy. What do we call the energy as? Resonance energy or resonance stabilization energy. So what is it? It is the energy difference between the most stable canonical form, in case of benzene, what is it? Kekulé structures, and the resonance hybrid. So this talks about what is the amount of stability that resonance is able to bring to the compound. Okay. And in organic chemistry we will see, whenever the resonance phenomena has to be disturbed for the benzene ring, it will be very difficult, because if the resonance phenomena is disturbed, right, the resonance amount of energy, the resonance stabilization energy has to be given back, means the energy of that entire molecule will be what? Increasing. So that is the reason why you will see that the benzene will not participate much in chemical reactions of the type where it will lose the resonance phenomena inside the benzene ring. Okay. Now the other thing about resonance is that resonance will be able to average out the bond characteristics. This is something that we have been seeing from the first example that we discussed, isn't it? So in the case of ozone, what did we observe? That the bond characteristics are getting averaged out. So what did we say? The bond length will be what? It will be 128 picometer, which is in between 121 and 148, isn't it? And similarly the bond order also is what? Nearly 1.5, which is in between that of a single bond and double bond. Bond enthalpy values also will be what? Averaged out. So resonance, while it brings stability for the molecule, it also averages out the bond characteristics. Okay. So these are some of the important aspects that we need to consider about the phenomena of resonance. Now again, the level of application of resonance we see in inorganic chemistry will be kind of limited to few examples, but we will have an extensive study about resonance phenomena and the applications of it when it comes to organic chemistry, and particularly certain organic compounds, the compounds which we will be calling as the aromatic compounds. Okay. So again we will talk about the resonance phenomena over there, but with regard to the chemical bonding, right, this is sufficient in terms of understanding what is the concept of resonance.